So we're going to look at some checks for convergence of series. But before we do that, we're just going to go back to our limits and refresh our ideas about limits, because we're going to have to use limits to check for these convergence and divergence of these series. So basically, when we have 1 over n, as n goes to infinity, the limit is 0, so we know that one. This one we know that if we have strong over weak, weak over strong, we know that the limit goes to infinity. Okay, so these strong over weak arguments are useful for when we have limits to infinity. Okay, it's equal to 0. This one here we may or may not have gone over, but this one is one that we should get to know. So the nth root of n is going to be equal to 1. For this one here, if we take the nth root of any number, okay, as long as x is greater than 0, if we take this root, just keep on rooting, eventually that number will tend towards 1. This one here, as x goes to, or n goes to infinity, for any geometric series, we know that as long as x is less than 1, it will tend to 0. This one here is how we generated our e function. This is essentially the compound growth formula. As we compound continuously, we generate the continuous growth e base. Okay, as we let n go to infinity, this will end up being e to the a. And then for this one here, again, this is actually related to this one here, where we have, for large values of n, we have weak over strong, because we have the relative magnitudes of functions here. And then this one is, again, one that we need to remember. This is different. This one's different than the other ones. This one's, as n goes to 0, of sine n over n is equal to 1. And that one's used sparingly, but we will use out. We need to kind of make sure we know our basic limits. So since we are looking at infinite series, we can start using this relative strengths of functions a little bit more. So the weakest function is log n. The strongest is n to the n. We have a p series in here where we have the roots, we have our harmonic series, and we have our, when p is greater than 1. Okay, these ones are like ones like the Basel series where we have 1 over n squared. Our geometric series or exponential series, and then our factorial ones as well. And again, this is, if we can use our strong over weak arguments, this is a place to use it. As x goes to infinity or n goes to infinity, we can use our strong and weak arguments for these ones when we do limits. So we can prove this one here. This one's related to this n to the nth root of n. So as we let n go to infinity, okay, this always tends towards 1. Okay, and we can prove this. So we can do this using L'Hopital's rule. So we have this limit here. We have a power. Okay, so we need to be able to bring that power down. So we're just going to start with our log form. So we're going to say log y is equal to 1, the nth root of a n plus b. Okay, and so if that's the case, we're going to say that the limit, this is going to be equal to the limit as n goes to infinity, and we'll write this in the ratio form, log a n plus b over n, and we can see that we have, as n goes to infinity, the numerator is infinite, the denominator is infinite. We have our condition to apply L'Hopital's rule. Okay, so applying L'Hopital's rule, we end up with the limit as n goes to infinity. This becomes 1 over a n plus b times a on top. Okay, on the bottom it just becomes 1. Okay, so there's our limit. We can now evaluate our limit. Okay, this is going to be equal to a divided by infinity. So a divided by infinity, our limit is 0. We can evaluate that limit. So we can establish that log y equals 0. And then we can say that y equals e to the 0, which is equal to 1. There's our result. Okay, so we know that based on this limit, we can say that n to the power n always tends towards 1. Okay, and we've now proven that using L'Hopital's rule, so we can establish this limit here. Okay, the nth root of n is always equal to 1. Okay,